We now turn to processes that interact by means of communication over channels rather than using shared variables. Let us consider the example of two producers that want to communicate with two consumers. We would like that producer 1 communicates with consumer 1, and similarly for producer 2 and consumer 2. Communication is by means of a shared channel and a multiplexer and a demultiplexer. In this version of guided commands, we need an output operation expressed with an exclamation mark for sending the value of an arithmetic expression A on a channel C. And we need an input operation expressed with a question mark for inputting a value on the channel C and assigning it to the variable X. Clearly, input and output may be used as ordinary commands. However, we shall also allow them to be used in guards, in conditional, and in a restricted version of the iteration construct called loop. Focusing on the multiplexer and demultiplexer, they can be written in guarded commands as shown here. At the top we have the multiplexer that simultaneously listens on channels in 1 and in 2, and sends a coded version of the message on the channel CH. At the bottom we have the demultiplexer that listens on channel CH and decodes the message to see which output channel it is intended for. We are here using integer division and the corresponding remainder operation. The program graphs obtained are shown here. Note that output and input have become actions on edges in the program graph. Let us now consider the generation of program graphs. For output and input, it should be no surprise that they give rise to a single edge. For conditional and iteration, we have the familiar construction from previous chapters. For the loop construct, we simply proceed as in the do construct, except that we have no edge labeled done. For the semantics, we need to modify our configurations. We need a buffer for each channel, so that output can place a value in the buffer and input can remove a value from the buffer. Ignoring arrays, our memories just map variables to integers, whereas our buffers map channels to lists of integers. We now define the semantics of actions. This will be a partial function mapping memories and buffers into memories and buffers. For the output action, we first evaluate the arithmetic expression and then append it to what is currently in the buffer for the channel. For the input action, we take the first element of the buffer and assign it to the variable. Note how similar these actions are to the one for assignment. In all cases, we sometimes produce undefined whenever the arithmetic expression is undefined or the buffer or variable is not as required. We construct program graphs as before. Our configurations contain a node from each of the parallel processes together with the memory and the buffers. An execution step relates a start configuration to an end configuration. The execution step is labeled with the action performed. The end memory and buffer is obtained from the start memory and buffer as described by the action. There are alternative versions of the semantics that you may consider. The most obvious choice is to limit the size of the buffer, in which case one needs to determine what happens when outputting to a buffer that is full. You should now use the online tool to construct an execution sequence for the multiplexer scenario. You should make sure to initialize the buffers for in1 and in2 appropriately. Next, extend the system with producers using suitably initialized variables u1 and u2 and buffers that are empty. Note that the online system allows you to put limits on the buffer size. Try to experiment with that and see what happens. Finally, you may extend the system also with the consumers. Having done this, you should read the section in the book, Doing the Try-it-outs on the Way.